times sine of that infinitely large value, then what I see is this red curve where I've got a sine curve that's decaying down as it gets closer and closer to 0, and then it's expanding upward. Now, notice when I get closer and closer to 0, how many of those up and downs are there? Infinitely many of them. So within an infinitesimally small x value, I have infinitely many y values. So that means it's impossible to evaluate this function by just saying, okay, what's the left-hand limit, what's the right-hand limit? That doesn't work. So what we're going to do is we're going to construct a function that's going to be above my red function and a function that's going to be below my red function. And the goal is to know the limit of these functions we construct. We want to know the limits at x equals 0. Well, so what we do is we say, let's let the above function, the yellow function, be y equals x squared. And we know that the limit, as x approaches 0, of y equals x squared is 0. And then the lesser function is y equals negative x squared. So we know that the limit as x approaches 0 of y equals negative x squared is 0 also. Now here's the other thing we know, is y equals x squared has to be greater than or equal to y equals x squared times sine over x anytime. Why do we know that? Because we know that sine of anything has to be between -1 and 1. Remember the sine curve. Goes up to 1, down to -1. So that means sine of anything has to be between -1 and 1. Well, that means sine of 1 over x has to be between -1 and 1, and could equal -1 or 1. Now, if I take that inequality and multiply through all three pieces by x, or by x squared, then I end up with the inequality negative x squared is less than or equal to x squared sine 1 over x, which is less than or equal to to x squared.